Hello, I'm Zheng. I'm a professor of computer science at the Oxford Brookes University, United Kingdom. I'm presenting the research paper on automation of datamorphic testing. It is co-authored with my colleague, Dr. Bayley, Dr. Dongmei and Mr. Xiaoyu Zheng. Datamorphic testing is a methodology for testing AI applications we proposed a year ago at the same conference on AI testing. It is based on our analysis of the causes of the difficulties in testing our applications by using Lemma's theory of software engineering. Lemma identified the three kinds of software uncertainty, which are the driving forces for the software evolution and also the focus of software quality assurance and testing. We identified the new features of AI applications in all three different types of software uncertainties in Lemma's theory. We have also identified a new type of software uncertainty, which is called algorithmic uncertainty. It is caused by the randomness in the algorithms used to develop AI applications and also the randomness in the operation of AI applications. Addressing these problems, we proposed datamorphic testing as a new framework for test automation. It is based on the concept of datamorphisms, metamorphisms, and seed test cases. The methodology starts with the analysis of software requirements to derive these three kinds of key elements in test automation and to implement them as test code, therefore they can be automated. We have conducted a case study in our previous work by using the testing of the face recognition applications as the subject. The key elements in datamorphic testing in our previous work consists of seed test cases, which are tested data generated from other types of test entities involved in software testing. For example, from programmer under test selected from the existing profile of recorded real data or random samples from the training data used for machine learning. Seed makers are such functions that generate seed test cases. Datamorphisms are transformations of existing test data to generate new test data. It is borrowed from our previous work called test data mutation operators. The test cases generated using datamorphisms are called mutant of the original test data. Metamorphisms are assertions about relationships between the original and the mutant test data, which could also involve the use of the outputs from the program on the mutant and original test cases. It is worth noting that metamorphisms are closely related to the concept of so-called metamorphic relations in the metamorphic testing techniques. Metamorphic relations are nothing but a spatial form of axioms in algebraic specifications, so they are powerful to specify software functionalities. Metamorphic relations can be converted to metamorphisms in a more algebraic way, therefore they can be used as a test oracle. The basic ideas of metamorphic testing can be summarized in the following form. For different aspects of software testing, the difficulties caused in these kind of testing aspects, we have the proposed solution in datamorphic testing. For example, test case generation is difficult for testing AI applications because the test cases are very complicated. They are needed to be very realistic, and we need a lot of test cases. Datamorphisms can be applied to seed test cases to generate realistic mutant test cases and give a large volume of learn and to deal with the complexity in the test data. For test oracle problems, the problems are caused by the lack of formal specification for the applications and the results are hard to judge whether it is correct or not by the human testers, and the requirements for such applications are changing frequently. So we proposed to use metamorphisms to check test correctness based on the metamorphisms general mutant test cases. Test coverage is difficult for testing AI applications because the AI applications are not usually in the structure of the source code, and the data space is often very difficult to describe, and the distribution of the data on this space are often unknown. So we use datamorphisms and seeds to define the algebraic space for the software data space, and we can measure the coverage accordingly. Testing AI applications are widely known to be very expensive, sometimes prohibitive for the manual testing. It is because of the existing test automation techniques not usually applicable for AI applications, and we need to repeat the testing many times each time we learn new algorithms from machine learning and so on. So the proposal we have for the datamorphic testing is to implement and reuse the seed makers, datamorphisms, and datamorphisms as well to achieve reusability and achieve test automation. So from description of ideas, you can see we have a number of hypotheses underlying the datamorphic testing method. First of all, datamorphisms, seed test cases, and the metamorphisms, we assume they can be systematically derived from the analysis of the application domain. Moreover, realistic test cases are supposed to be available as a result of other software engineering activities, for example, in the machine learning as the sample data in the learning algorithm. But these kind of test cases are very rare and sometimes inadequate and very expensive to obtain. We assume that more test cases which are supposed to be realistic can be generated by developing and applying datamorphisms on seed test cases, even for structurally complicated input data space like AI applications. These hypotheses have been validated in our previous work using the face recognition application as a case study. But there are more hypotheses we need to validate in order to prove the method is a valid method for software testing. First of all, we assume test adequacy can be achieved through combination of datamorphisms on well-designed seed test cases. Second, test cost should be reduced by implementation and application of datamorphisms and metamorphisms. They should be useful to automate test processes. They should be relatively easy to develop with low cost, and they should be reusable. These hypotheses are the goals for this paper to validate. So the main contribution of the paper can be summarized as these 3 points. First of all, we're going to generalize the framework of datamorphic testing to be useful for automate the testing process. In particular, the general theory of datamorphic testing is to classify the artifacts of software testing into 2 types of things. One is called test entities and another is called test morphisms. I will give definition of this concept in the next slides. Second, we have designed and implemented an automated testing framework called Morphy based on this general theory of datamorphic testing. I will show you how test entities and test morphisms can be specified in a declaratively imperative approach, and how to automate testing at 3 different levels. First is in the activity level, and the second is in the strategy level, and on top of all of them is a process level. I will show you how to implement test strategies in this framework. The details are given in the paper. In particular, we propose a set of datamorphic test strategies for AI applications. They are formally defined and their algorithms are proved correct. They are implemented in Morphy, and we conducted a case study to demonstrate how they are used. The general theory of datamorphic testing classifies the artifacts of software testing into two types. One is entities, one is the morphisms. Entities are objects and data used or generated in testing. Typical examples include test cases, test sets, program under test, test reports, bug reports, etc. Test morphisms are mappings between test entities. They generate and transform test entities to achieve testing objectives. They can be implemented by writing test codes, and they can be invoked to perform test activities and composed to form test strategies and test processes. Typical examples of test morphisms are test case generators, data morphism, test oracles, such as metamorphisms, test set optimizers, coverage metrics, test report generators, mutation operators, and many others. For example, there are other examples of test morphisms we found particularly useful for the test automation. First of all is a test case matrix, which are mappings from test cases to real numbers. Test case filters are mappings from test cases to choose values or Boolean values. Test set metrics are mappings from test set to real numbers, like test coverage. Test set filters are mappings from test set to test set. For example, those algorithms to reduce test cases for a subset for regression testing are test set filters. Test executors are mappings from program on the test to a mapping from the input to the output. They are achieved through the execution of the program on the test on test cases and to receive the outputs from the program. From a mathematical point of view, they are functors in the category theory. Test result analyzers are mappings from test set to test reports too. Morphy is a software tool we have developed based on the general theory of datamorphic testing. It provides a formalism for the specification of test systems, which is defined as a set of test entities and a set of test morphisms. So the formalism defines the format, operations, and instances of test entities. The definition of various kinds of test morphisms are defined in the form of methods and used for the testing. Morphy provides a number of functions to the management of test systems. Testing automation has been achieved at 3 levels. At activity levels, it is achieved by invocation of test morphisms implemented as test code. At the strategy level, Morphy defined and implemented a set of test strategies. They can be evoked by the user through selection of parameters and the strategy to apply. At the process level, the interactive uses of the tool can be recorded to generate test scripts. And these kind of test scripts can be edited and then replayed again and again. So achieve the test automation at a very high level of abstraction. Morphy's specification of test system is what we call the declaratively imperative. Each test specification is a test system which is a Java class, which declares a set of attributes as the test entities and a set of methods as the test morphisms. The test entities use a generic class called test case to represent the test cases, and also a generic class called test pool for representing test suite or test set. Test morphisms and test entities are annotated with metadata using Java's metadata mechanism. Here is the table describes what type of test morphisms are annotated with what kind of metadata and the structure of the metadata. The Morphy consists of three key components. The first component is to manage the test entities and test morphisms. The second component is a test runner, which executes the test morphisms, executes the test strategies, and to manage test morphisms. The third component is a test script facility, which supports the recording of the test script, to manage and editing test scripts, and to execute test scripts. These are supported to use a graphical user interface, so the user can evoke the functionalities with a click of buttons. This is the picture of the graphical user interface. On top of them are the buttons to implement various types of functions of the tool, and the bottom part is the information for the testing system. So the information panel lists all types of test morphisms, and the user can select test morphisms for use in the testing process by clicking on the checkbox for test morphisms. This is a message panel which gives the information about what is executed for the testing. The error report panel reports the errors detected by testing. The management of test system consists of a number of buttons to load the specification, to load the test set, to save test set, and to clean up the state of the system. The activity level test automation is supported by a set of buttons which you can click to evoke corresponding test morphisms. The test set can be viewed and edited in this window, where each test case can be measured using the test case matrix. The strategy level automation is supported by a function which you can select this test strategy and to select the parameters for the test strategy and to execute it automatically. At the process level, there is a set of buttons for create a new test script, to load previously saved test scripts, to start recording interactive test activities, to play the current test script and the save test script to file, view test script, and also for editing it, and also you clean the recorded test script, and so on. Here is an example of test script, and you can see it consists of high-level functions recorded in the testing process. Clean is to clean up the state of the system, is a management function. Make seed is evocation of the seed maker. Run and walk is a test strategy. It gives the parameters of the strategy. Analysis is the function calling for analyzers. So let's focus on the test strategies. Generally speaking, a test strategy is a rule which determines when, what, and how a testing activity is to be performed by who and to which test entity. It is equivalent to a rule to determine when a test morphism should be applied to which test entity with what kind of parameters. So we can see the test strategies can be defined in the form of an algorithm which describes the composition of test morphisms in a complicated way. These kind of strategies are very useful to maximize the test effectiveness under certain restrictions of test cost and to achieve balance between test adequacy and test cost. We have defined a set of test strategies for testing AI applications. Here we focus on the so-called mutant combination strategies. These type of strategies are most useful for testing AI systems because we use seed test cases to test the normal operation condition of an AI system, and we use datamorphisms to transform test cases to represent abnormal or other operation conditions which can be derived from the normal operation conditions. This is the methodology we proposed in our previous work. So combinations of datamorphisms means the combination of different operation conditions. For example, for the testing of face recognition applications, we can use datamorphisms to transform images to adding makeup, wearing glasses, changing skin tones, changing hairstyles and the colors, even the changing of the age. We can also use datamorphism to represent different operation conditions of the face recognition system. For example, the angle of camera could be different, the lens could have a distortion, the background could change, the illumination, the lighting, the weather condition, all these things can be represented by datamorphism to change. The combination of all these kind of things means a combination of different operation conditions. Even for testing driverless vehicles, we can use datamorphisms to represent weather conditions, for example, adding fog into recorded driving process. It can be used to transform the lighting condition from daytime to nighttime with street lights, etc. So combination of these kind of things will be in daytime with fog and nighttime with fog, etc. So present the kind of combination of operation conditions. The first strategy can be defined as a test adequacy criteria in the form of you need to cover all first-order mutants. Here, the first-order mutants are test cases derived from seed test cases by applying one datamorphism. So each first-order mutant test case represents one operation condition of the system. So the adequacy criteria we want to achieve is to cover all first-order mutants in the testing. In the paper, we have formally defined this adequacy criteria, proposed an algorithm for generating the minimal set of first-order mutant adequate test set. We proved the correctness of algorithms, and there are also examples to illustrate the use of the strategy. First-order mutants does not cover all the combinations of the operation conditions. Therefore, we want high-order mutant coverage. Here we define a case-order mutant test case as follows by induction on the K. A seed test case is 0th order mutant test case. A K+1th order mutant test case is generated from a mutant test case of case order by applying one datamorphism. So a case order mutant test case represents a combination of K operation conditions. Test adequacy criteria can be defined as follows. A test set of case order mutant is complete if it contains all mutant test cases of order n for n less than or equal to k. The case order mutant complete test set means the test covers all k combinations of operation conditions. In the paper, we give the definition of the criteria formally and an algorithm to generate the minimal set of test cases, that is a case order mutant complete. The algorithm is proved correct. Here, give some examples of first order and higher order mutants. Photo A is the original photo. Photo B, C, and D are the first order mutants obtained by adding a pair of spectacles, wearing a makeup, and changing hairstyle. Photos E, F, and G are second order mutants. They are obtained by applying datamorphism B and D, C and D, and B and C respectively. Photo H is a third order mutant, which is obtained by applying all of these mutant operators B, C, D. From the example, you can see if we have three datamorphism methods, then if we have the third order mutant complete, you have covered all kinds of possibilities of combination of them if the datamorphisms are associative, commutative, and distributive, and idempotent. Here, a permutation complete test set we can define as a test set that contains n for a set of datamorphisms that contains n methods. It is nth order complete. If the datamorphisms in this set of D has these kind of algebraic properties, we know a permutation complete test contains all possible test cases that can be derived from a given set of seed test cases. Therefore, this kind of test case is exhaustive with regard to the set of seeds and datamorphisms. This illustrates the concept of combinations of datamorphisms, and we can further define the combinatorial coverage of mutant test cases. We ignore the details in this presentation. The authors are referred to the paper for the details. We have conducted a case study to validate the hypothesis we given at the beginning of the paper. So the aim of the experiment is to demonstrate the usability of testing tool Morphy and to demonstrate the computation strategies proposed in the paper can generate adequate test sets. The particular research question we address here are whether the test morphisms are easy to write or difficult to write. Are test morphisms reusable? And can test morphism be combined in different ways to enable different test strategies to be applied? We use three sets of subject programs. The first is triangle classification. We have two different algorithms to implement it, and plus mutants to inject the faults into the subject. The second is a set of three functions of trigonometric functions, sine, cosine, and tangent. And the third is a set of face recognition applications. We actually have four different applications. For each of them, we applied different kinds of test strategies to validate how easy to apply those test strategies. The experiment process starts with the development of test system that consists of seed makers, datamorphisms, metamorphisms, and test result analyzers and test executors. Here, the face recognition, we do not use metamorphisms because in our previous work, we have shown all these face recognition applications are correct in terms of they can identify the right person. So we use a statistical analysis of data to see the scores of the test result. So the result analysis is particularly useful for face recognition. After developing the test system in Java, we apply the test strategy to generate test cases, then execute subprograms on the test cases on all different variations of the programs, and then to apply the metamorphisms to check the test correctness, except the face recognition, as I explained earlier. Application test results are analyzed to report the test results. This process is recorded to generate a test script using Morphy's test script facility, and the test script is then executed repeatedly at least twice to automate the test process and to check if process can be automated. Here is a summary of the experiment data, which shows the size of the test specifications, and for each type of different test morphisms, the complexities, and so on. From the data, we can find the following conclusions in the case study. First of all, writing test morphisms are very easy. The lengths of test morphisms are very small, and you can see from the data in the previous slides. And the codes are almost all very, very straightforward. The test morphisms are very reusable as well. For all subject programs, test morphisms are reused for different testing strategies without any change. For face recognition applications, for example, data morphisms analyzers are reused for testing 4 different applications, although they have different formats of input and so on, and different formats are output as well. We do not need to make changes for data morphism analyze. Only the executors are different, but which are all very simple to write. Essentially, the submit request to the website. A new type of testing for the face recognition has been realized by writing a new seed maker. We don't need to change any other test morphisms. From the testing, we also notice the test is effective, although evaluation of the test effectiveness is not our purpose. We observed that faults in the faulty versions of triangle classification programs can be detected by the generate test cases, and the inaccuracy problems in trigonometric functions can be detected in our testing. Our work can be compared with existing test automation frameworks. Typically, we have 2 types of these kind of test automation frameworks available in the literature. One is called the X-unit architecture. One is the so-called GUI-based test frameworks. Both of them are with limited applicability to test AI applications because they do not address the main difficulties of testing AI applications. There are no explicit use of the notions of test entities and test morphisms. It is difficult to reuse and very difficult to evolve in these 2 types of test automation framework. And also their test scripts are very low level in comparison with our work. Test automation framework, as we presented in this paper, they can be used to integrate various types of test automation tools we developed in the research and used in the practice as well. For example, test case generators like fuzzers for test metrics and coverage measurement, they can be easily integrated into our automated testing too. We are further working on this direction at the moment. We have already developed 2 other types of test strategy which is not reported in this paper. The first type is the so-called exploratory test strategy for testing classification type of AI applications. This has been reported in the paper here at the first IEEE ACM conference on automation of software test as a part of IEEE. We have also implemented a set of test strategies to optimize the test sets using generic algorithms. This will be reported separately in another paper. We are also conducting more experiments and case studies with other types of test strategies and so on. Thank you.